All right, today we're going to break down a process that is quite literally a lifesaver for millions of people, dialysis. We're going to dive into what it is, how it works, and maybe most importantly, why knowing about it is so incredibly critical. So let's get right into it.
So, I want you to just picture for a second the most amazing high tech filtration system you can possibly imagine. It's working inside you 24/7 without you even thinking about it. That's your kidneys. But what happens when that perfect system just stops? What do you do when the body's master filter fails? And that, right there, is where the problem starts. See, when the kidneys can't do their job anymore, whether it's from disease or a sudden injury, the body loses its ability to clean itself. All that waste, all those toxins, and all that extra fluid, it just starts to build up. And we're talking dangerous, life-threatening levels. It creates this absolutely critical need for an outside solution, an artificial replacement.
So, who are we talking about here? Who relies on this? Well, it's actually a pretty wide range of people. You've got patients with end-stage renal disease, which is when their kidney function is pretty much gone for good. But it's also for folks with acute kidney injury. That's a sudden failure, maybe from trauma or a bad infection, and sometimes it's even temporary. And, it's also used in real emergencies, like to fix severe electrolyte imbalances or even for certain kinds of poisonings.
So, if your body's natural filter is offline, what's the plan? Well, we have to build one. And this is where the absolute marvel of medical technology just steps right in, creating an artificial kidney that's ready to take over the job. And that's really the core of it, isn't it? When you boil it all down, that's our definition. Dialysis is simply an artificial replacement for the kidney's filtering function. It's important to remember it's not a cure, right? It's a mechanical process, a machine that does the essential work that the kidneys just can't do anymore. Okay, so we know it's a replacement filter, but what's it actually filtering? What is the trash that it needs to haul out of the bloodstream to keep someone healthy and alive? Well, let's take a look at the hit list. And this machine is incredibly thorough. It pulls out metabolic waste products like urea and creatinine, stuff that can become toxic to your brain if it builds up too much. It removes excess water. And super importantly, it balances electrolytes like potassium and sodium. I mean, if those get out of whack, it can mess with everything from your heartbeat to how your muscles work. It even helps get the body's pH right by removing acid. It's doing a lot. And believe me, this isn't just some abstract science concept. The consequences are so real. Just take that one job, removing excess water. Without dialysis doing that, fluid would start to back up into a person's lungs. That condition is called pulmonary edema, and it is a true life-or-death medical emergency. Dialysis directly stops that from happening. So, how in the world does this machine actually pull off such a complex cleaning job? The technology sounds like something out of science fiction, but it's really based on some beautifully simple, fundamental scientific principles. It's all about mimicking the body's own amazing design.
Check this out. It's really just a clever, engineered version of a natural process. So, where your kidney has its natural filtration system, the dialysis machine uses a special, man-made, semi-permeable membrane. To get rid of all that waste, the junk solutes, it uses a basic principle from chemistry class called diffusion. And to pull out the extra fluid, it uses a process called ultrafiltration. It's just mirroring biology. Let's walk through it step by step. First, blood is gently pulled from the patient and flows into the filter, which is called a dialyzer. Now inside, the blood is separated from this special cleaning fluid, the dialysate, by that semi-permeable membrane we talked about. The best way to think about it is like a screen door. The big, important blood cells are too big to get through, but all the tiny waste products get pulled across because of diffusion. They naturally move from where there's a lot of them, in the blood, to where there's none of them, in the clean fluid. At the very same time, pressure is used to gently squeeze out the excess water. And then, the clean blood is returned right back to the body. Pretty amazing.
Okay, understanding the mechanics is one thing, but knowing what's at stake in the real world, that's a whole other level. For paramedics, EMTs, and other first responders, this information isn't just academic trivia. It is absolutely critical in an emergency. And here is the single most important point. For a patient who relies on dialysis, those treatments are their lifeline. A single missed appointment means all that waste, all that fluid, all that potassium, it's all building up again. This isn't just some inconvenience. It can spiral into a life-threatening medical emergency fast.
So first responders basically have to be detectives. If they show up and a patient is short of breath, their mind should immediately think, could this be fluid overload from a missed dialysis appointment? If they see really specific things on an EKG, like these sharply peaked T waves, that's a classic red flag for hyperkalemia, which is dangerously high potassium. And they've got to be on the lookout for other things too, like low blood pressure after a treatment, or problems with the access site, like bleeding or signs of infection. These are all critical clues. At the end of the day, for a paramedic or an EMT, being able to connect those dots, recognizing these specific signs, and knowing the patient is on dialysis can make all the difference in the world. It leads to a much faster, much more accurate assessment, and that can absolutely save a life.
Phew, okay, we have covered a ton of ground here. The why, the what's, and the how of dialysis. So now let's just boil this entire thing down to its absolute essence. The one sentence you really need to take away from all this. So if you remember just one thing from our discussion today, what should it be? What's the real bottom line here?
Here it is. Dialysis filters waste, fluid, and electrolytes from the blood, replacing the kidney's essential functions in renal failure. That is the whole thing in a nutshell. It's an artificial replacement doing the essential, life-sustaining work of an organ that has failed. Simple as that.
And that kind of leaves us with one last question to chew on. We've gone from having no solution for this problem to this incredible machine. But what comes next? As our technology gets smaller and smarter and more sophisticated, what could the next generation of the artificial kidney even look like? A wearable device you have on you all the time? Maybe an implantable, bio-artificial organ? The future here is going to be incredibly exciting to watch.